So let's look at the composite of this guy right here. And we have 400 millimeters from this edge to the bottom, and the piece is 100 millimeters thick. So this would be 300 millimeters. We need to know the center of mass of this composite piece right there. Well, that'd be 150 plus 50, or 200. Okay, same thing on top. The distance from this center of mass is going to be 200 also. Okay, and we know the formulas. Moment of inertia about the center of mass, 1/12 bh cubed. The width times the height cubed. Let's see. Composite part number 1, composite part number 2, composite part number 3. Okay, first thing to note about this is the total width here to here. Just a reminder, 600 millimeters. So we can see where all the numbers come from. We already figured out this point right here is 200 millimeters. So, moment of inertia about the x-axis for both rectangles A and D. I would have called them 1 and 3. Is moment of inertia about the center of mass 1/12 times the width times the height cubed. And we can see that instantly right there. Plus the area, 100 times 300, that's the area of D or A, times the distance from the center of mass squared. Boom, we got it. Now, 1/12, in this case, the width is 300 and the height is 100. When we're talking about the y-axis, the width is this direction and the height is this direction. Plus area, 100 times 300, just like before. Here's where the 250 comes in. That half the width of this metal piece is 50 millimeters. Total width is 600, so it's 300 from here to here. Take away 50. 300, take away 50. 250 squared. Crunch the numbers. That gives you Ix and Iy. For each one individually, we have to double it to get the moment of inertia of the two, of A and D together. Now, looking at part B, rectangle B. Well, that's a lot easier because the coordinate system is sitting on the centroid, or the center of mass. So it's 1/12 times the width, 600 times 100 cubed for the moment of inertia about the x-axis. The y-axis, 1/12. Now the width and height are reversed. The width is 100, the height is 600. And here's where that 2 comes in. 2 times A or D equals A plus D, plus this guy, and then this plus this. 1.8 times 10 to the 9th is this guy. Okie doke. Now we need to talk about product moment of inertia. So this is important because we need to find the location of an orientation of coordinate axes to maximize or minimize a moment of inertia. So if you spin about one axis, you'll have a large moment of inertia. If you spin about another, you'll have a low. And the example here is just a thin rod, that it has a high moment of inertia about the y-axis, low about the x-axis. And here's the formula right there. It can be zero or positive. Ix and Iy can be zero or negative. And the only way it can be zero is if it had no dimensions and no mass. Ixy can be negative because x could be positive, y could be negative. If the object is symmetric, and here's an example right here, this guy here, and this is, I just drew the symmetry axis. If it's symmetric about either axes, then the product moment of inertia is zero. This sign changes with the quadrant. So this drawing illustrates that the integral xy dA will change sign depending upon which of the four quadrants it's in. And units are length to the fourth, meters to the fourth, millimeters to the fourth, foot to the fourth, just like Ix or Iy. Now we need to talk about the parallel axis theorem for product moment of inertia. Very similar reasoning to the moment of inertia, the regular moment of inertias, Ix and Iy. So here's the definition of product moment of inertia. We put in for x, x prime plus dy, which is, for x. X prime plus dx, x prime plus dx. Dx is here, x prime is here. So this is the location in the xy coordinate systems of the point under consideration. And of course y prime is going to be the dy plus the y prime. And we know, or presume, anyway, we want the relationship between the moment of inertia in the primed axis, which is the origins at the centroid, or the center of mass. Ixy, then, we can work this out. We expand the binomial, we get these expressions here, and this, of course, is dx dy times a. This integral is just the area. This is the product moment of inertia about the center of mass. And that's the first term, the last term. These two terms, just like before, C is the center of mass. So the integral of y prime dA is going to be 0. Integral of x prime dA is going to be 0. Because the center of mass is at 0 in both cases. And there it explains it right there, resulting in this. The yellow highlighted stuff that I use, those are things to take good notes about. So previous slides and this slide, you should probably have this written down on a note card somewhere to refer to quickly.